In this lecture, we will learn about Lowa's local lemma. Lowa's local lemma is a tool that can be used while we apply probabilistic method. So, while using probabilistic method, we often have to show that probability of a certain good event is greater than 0. So, now this can be done in a wide variety of ways. How do we describe this event E? So, E, if we think of as a good event, we could say that this good event happens when a list of bad events does not happen. So, let us say if our bad events were E1, E2 up to En, and if we call this as the bad events, in order to say that the good event happens with a positive probability, we could also say that probability of any of the bad event happening is less than 1. Okay, that means there is a probability that the good event happens. So, we look at E as, we can simply write E as E1 union En. This means one of the bad events is happening. The complement of it means none of the bad event happens. So, that is equal to intersection over I Ei complement. So, instead of saying that the good event happens with positive probability, we will say that the probability of this intersection, this is going to be greater than 0. So, when can we say such a thing? So, depends on these events. So, let us see what are some of the common assumptions that we could make about Ei. And one way to look at this would be if we thought that we knew nothing more about the events, just that they all belong to the same underlying probability space, we could use union bound. Okay. So, probability of E complement or E bar, we want to say that that is less than 1, this would imply that probability of E is greater than 0. If we want to say this, we could use the union bound, and it can work in some cases, but in many cases when these EIs are not too small and or when there are too many such bad events, if we apply union bound, we might not get any useful result. Another case is when the events are independent. Okay. So, when these events are independent, then we can say probability of intersection of I over Ei complement, this is equal to probability of each of the individual Ei, and you take product over them, I going from 1 to n. So, if each of these events, if at least one of those events happen with probability less than 1, we know that the product is going to be less than, if Pi is greater than 0 is the only assumption that we would need, Ei complement is greater than 0. But independence is a very strong requirement. If the bad events are independent, so are their complements. The probability that one of the bad events occur, we can bound it by using independence. Okay. So, now when there is some amount of limited dependence, even then we can use probabilistic method, and that is what Lowa's local lemma tells us. Okay. So, what does it mean to have limited dependence? We will get to it, but before that, in order to specify this notion of dependency, we need something called as dependency graph. We need the concept of mutual dependence. So, these two concepts we will first learn. Okay. We would say that events A and B are independent if probability of A intersection B is equal to probability of A times probability of B. This is the definition of independence. We will say that if you have a collection A1, A2 up to AK, they are independent if mutually independent if you take any subset, this is equal to probability over I going from 1 to j. Okay. you take any subset of these events, if their probability, the probability that all of them happens is equal to the product of the probabilities, then we will say that these are mutually independent. We will modify this definition of mutual independence, and we will say when is one particular event mutually independent of a set of other events. We could also cast this mutual independence in terms of conditional probabilities. So, A is independent of B if probability of A given B is equal to probability of A. Okay. This is because probability of A given B is probability of A intersection B by probability of B. Okay. So, they are the same thing. So, the definition of independence, you can take this as the definition or even this as the definition. Okay. We will basically work with conditional probabilities. In case of mutual independence, the new definition that we will have is as following: an event A said to be mutually independent of A1 to let us say AK if for all subset J of 1 to K we have the following condition: probability of A given intersection over J belonging to J A J is equal to probability of A. So, if you look at an event, we say that it is mutually independent of a collection of other events if the probability of A conditioned on any subset of that collection of events is same as the probability of A. In this case, we will say that A is mutually independent of A1 to AK. Okay. So, that is our definition. Now, we are in a position to state what is dependency graph. If we have a collection of events E1 to En, we could imagine a graph in which the vertices are these events. Okay. So, E1, E2, E3 up to En are the vertices of our graph, and we will say that this is a dependency graph for these events if, so that condition let me just write down, for any event EI, you look at the vertices to which it is connected, those we will call as the dependent vertices, and the non-dependent vertices are the other ones. So, these are the non-dependent vertices. So, for any EI, the non-dependent vertices or the non-neighbors in G will be such that EI is mutually independent of the neighbors. Okay. So, if you look at any particular event EI and if its neighbors are let us say EA1 to EAK, these form a collection such that EI is mutually independent of the non-neighbors. In other words, the dependency can be at most amongst the neighbors. The EI can be dependent on at most the neighbors of EI and not on anything else. Events and form such a graph, that is called a dependency graph of E1 to En. Of course, there could be multiple dependency graph. For example, if you take the complete graph, it is anyway a dependency graph on any collection of events, because there are no non-neighbors and therefore, there is no requirement, I mean no non-trivial conditions on dependency. Okay. So, now we know what are dependency graphs and we know what is mutually independent. Now, we are in a position to state Loa's local lemma. So, we have a collection of events. So, let E1 to En be events such that some conditions, and then under certain conditions, Lowa's local lemma will say that the probability of intersection EI complement is going to be greater than a certain quantity, non-zero quantity. So, let us write down the conditions first. First requirement is probability of each EI should be less than or equal to some p. The second condition says that dependency graph should have max degree at most say d. Okay. So, if you construct the dependency graph on E1 to En, every vertex should have degree less than or equal to d. And the third condition is a relationship between this p and d, E times p times d plus 1 should be less than or equal to 1. Okay. So, under these conditions, the probability of EI complement is going to be greater than or equal to 1 minus 1 by d plus 1 the whole power n. Okay. So, this is what Lowa's local lemma states. So, let us look at some cases. Suppose EI was, all the events were independent, then of course, this is not such a great bound, because the condition requires that E times p times d plus 1 is less than 1, and d when they are dependent, this becomes as large as n minus 1. Okay. So, E times p times n should be less than 1, but in that case we could have used this union bound itself, and here we get an additional factor of E. Union bound would have required p n is less than 1, but here we are getting an additional factor E. Okay. So, when there is lot of dependency, Lowa's local lemma may not be useful, but we will see that there are cases where the dependency is limited. In that case, this is a very handy tool to apply probabilistic method. Okay, we will first see a proof of Lowa's local lemma, and the proof will rest on the following claim. The probability of any EI conditioned on the none of the events in a certain set S has occurred. Okay. So, J belonging to S. So, let us say S is some set, and what this part says is that Ej bars have occurred for all j in S, that means none of the events in S has occurred. So, probability that an event I occurs, so this is our collection of all events, all bad events which we wanted to look at, and this one particular bad event occurs given that none of these other bad events have occurred. Okay. The claim says that this probability is going to be less than 1 by d plus 1. Under the assumptions of our theorem, the claim says that probability that EI happens given intersection j belonging to S Ej bar is less than 1 by d plus 1. We will prove Lowa's local lemma assuming this claim, and later on prove the claim. Okay. This claim is true for all S subset of, if your events were 1 to n, E1 to En, then you take any subset of 1 to n, for that the statement is true. So, Lowa's local lemma said that probability of intersection EI bar is going to be greater than or equal to 1 minus 1 by d plus 1 the whole raised to n. Okay. So, this event intersection I going from 1 to n ei bar, and so the probability of this can be written as a product involving conditional probability. So, if you think of the intersection as let us say A1, A2, AK, we could think of this as probability of A1 into probability of A2 conditioned on A1 into probability of A3 conditioned on A1 and A2 and so on. So, this is probability of EI E1 bar into probability of E2 bar given E1 bar into probability of E3 conditioned on E1 bar comma E2 bar and so on. The last would be probability of E, suppose there were n events, En bar conditioned on E1 bar, E2 bar, En minus 1 bar. There are going to be n terms in this product and each term looks like the complement of one of the events in the claim. Okay, so, this I can write it as 1 minus probability of E1 into 1 minus probability of E2 on the same condition into 1 minus probability of E3 based on the same condition and so on. And these events by our claim we know that they are going to be less than 1 by d plus 1. So, this quantity P of E1 is less than 1 by d plus 1. So, 1 minus that is going to be greater than, so this quantity is going to be greater than 1 minus 1 by d plus 1 and every quantity is going to be greater than 1 minus 1 by d plus 1. So, that gives us the lemma, the whole product is going to be greater than 1 minus 1 by d plus 1 the whole raised to n. So, if we assume the claim we are done, but we need to prove the claim. So, proof of claim, we want to show that probability of any event EI conditioned on a set of other events not happening j belonging to S E j bar less than or equal to 1 by d plus 1. Okay. We will prove this on by induction on size of S. So, let us just have a small diagram before that. This is our favorite event which we are looking at EI and this is our set of other events S. Okay. We were conditioning on that. Okay. We are saying that none of the events in S happened. Okay. This S we can split into two parts, let us say S1 and S2. S1 where the events to which E was connected in the dependency graph and these are the non-neighbors. We can split it into two parts. So, the conditioning over intersection we can write this as probability of E1 given, let us say, I will abuse the notation, I will write it as S1 the intersection over all these events. So, if S1 and S2 were the two parts of S, what we are doing is these were A, B and C and this is D, E and F. We have is A intersection B intersection C intersection D intersection E intersection F. Okay. So, we could split these two parts, you can think of this as let us say capital A or script A and this is script B. Okay. And instead of looking at these things we just call them as S1 and S2. So, it is basically S1 intersection S2. Okay. Here I am abusing the notation because S1 is you can think of it as an index set or you can just think of it as the collection of events. Okay. So, EI in given S1 intersection S2, okay, that is what we need to calculate. Now, S could be any subset of 1 to n. If S was the empty set, that would be our base case of our induction. If S was the empty set, this means the intersection of an empty set is a whole universe, that means you are conditioning on the entire sample space. So, the expression would be when S is equal to phi, LHS is equal to probability of EI, and probability of EI is less than some p, which we know is less than 1 by E times d plus 1, because we had the condition that E p times d plus 1 is less than or equal to 1, and therefore, this quantity is less than 1 by d plus 1. So, when S is equal to phi, we are done. When S is not equal to phi, we have some set on which we are some non trivial set on which we are conditioning. That set we have split into two parts, S1 and S2. S1 consists of all those events on which EI could be dependent, and S2 is all those events on which EI is not dependent. So, now probability of A given B intersection C can simply be written as probability of A intersection B intersection C by probability of B intersection C, which is same as probability of A intersection B given C into probability of C divided by probability of B given C into probability of C, and probability of C we can cancel off, assuming that that is a non-zero probability event, and then we have this particular expression, and that is what we will use to expand probability of EI given S1 intersection S2. So, this will be equal to probability of EI intersection S1 given S2 into probability of S1 given S2. Okay. So, this is the expression that we will need to simplify. Probability of EI intersection S1 given S2 into probability of S1 given S2. Now, the numerator is going to be less than or equal to probability of EI given S2 divided by probability of S1 given S2. The numerator EI given S2, since S2 are all the events in S2 are basically disconnected from E1 when you drew the dependency graph, or they are not connected by an edge, and therefore, we know that this probability is same as probability of EI divided by the denominator S1 given S2. So, this is because of dependency relations. Okay. We need to estimate or bound probability of S1 given S2. One thing to note in between is that if S1 was an empty set, that is, if everything was connected to only S2, then this probability would essentially be probability of E1, which anyway is less than 1 by d plus 1. Okay. So, if all the elements to which on which we had conditioned were not connected to EI, then we automatically have this. So, we can assume here that S1 contains at least one particular element in it, because if they were not, probability of EI conditioned on certain other events, and all these events are not connected by EI by an edge. So, this probability is equal to probability of EI, and that we know is less than 1 over d plus 1. So, from now on we can assume that there is at least a single event in S1. Okay. So, when we compute this probability S1 given S2, we can again apply iterated conditioning properties and write this as probability. So, S1 we called it as a set. Suppose the set contained B1 intersection B2 intersection BR, where each of these BI's is one of the E1 E2 ENs. Okay. So, if S1 was this, we could write this probability as probability of B1 given S2 times probability of B2 given S2 B1 into probability of B3 given S2, B1, B2 and so on. Note that the number of terms here is at most d terms, because S1 is the elements which were connected to E1, and we had the restriction that the dependency graph had at most d edges out of any particular vertex, and therefore there are at most d terms. And look at all of these terms, the conditioning is on a set whose size is strictly less than the size of S. Okay. So, conditioning is on a set whose size is less than size of S, okay, because they are subsets of S from which at least one element has been removed. So, we can use the induction hypothesis, and based on this we can say that each of these B1, so B1 now is some event of the form EI complement. So, probability of some EK complement given some other thing is going to be greater than 1 minus 1 by d plus 1. This is because what we know is probability of EK given this is less than 1 by d plus 1. Therefore, the complement event on the same condition is going to be greater than 1 minus 1 by d plus 1. So, product of the denominators is going to be, so let me just call this as the denominator. So, d is going to be greater than 1 minus 1 by d plus 1 the whole raised to d. Okay. And since the inner term less than 1, this is of course greater than 1 minus 1 by d plus 1 the whole raised to d plus 1, and this quantity is going to be greater than 1 over e, okay, because in the limit it becomes 1 by e. Okay. So, we can plug this into the original expression. What we will get is probability of the event that we were interested in is going to be less than or equal to 1 by e in the denominator. So, e times probability of some ei, okay, and probability of ei, that is going to be less than e times p, which by assumption is less than 1 by d plus 1. Okay. So, that concludes the proof of the lemma. Just quickly recap the key ideas in the proof. We had this lemma which says the probability of a bad event occurring conditioned on a collection of other bad events not occurring is going to be less than 1 over d plus 1. After we have that, we can just apply iterated conditioning to get our lemma. In order to prove the claim, what we did is we used induction. The conditioning was on a set of bad events. We split the set of bad events into events which depend on ei and events which did not depend on ei. If there is at least one event which depends on ei, then we could use as our induction case. If there was no event which depended on ei, then we can just simply say that our argument that these are mutually independent takes care of the lemma. When they were events, the degree bound on the dependency graph helps us get what we want. Okay. So, we will move on to an application of Lowa's local lemma. Okay. So, let us look at a k-sat expression. You can think of 3-sat, or maybe for the purpose of this lecture think of a 20-sat expression. That means the expression is of the form x1 or x2 so on xk or x20 and some similar expression and so on. So, each of this is called as a clause. There are a large number of clauses. Each clause has at most has exactly 20 literals in it. K-sat means each clause has exactly k literals in it. We want to know that there is an assignment to the variables which makes this expression evaluate to 1. Okay. We will use probabilistic method to show that in many cases the expression indeed evaluates to 1. Okay. So, theorem that we will prove is, if no variable appears in more than 2 raised to k minus 2 by k clauses. Okay. So, in case of 20 sat expression, that would mean 2 raised to 18 by 20. So, 2 raised to 18 by 20, that is approximately 2 raised to 20 by 40, 2 raised to 10 is about 1000. So, this is 10 raised to 6 by 40. So, you can think of as 25,000 and approximately 25,000. So, if you are looking at a 20 sat expression in which no variable appears in more than 25,000 clauses. So, that is a good bound, in the sense, I mean, if you have very long expressions, I mean, to imagine that there will be some variable which appears 25,000 times, okay, that is a huge number. So, if that requirement is met, that is, no variable appears more than 25,000 times, then we can guarantee that the expression is satisfiable. Then the k-sat expression is satisfiable. Okay, the proof is simple. So, first let us think about a possible proof. So, if you think of all these clauses, I mean, there are, let us say, m clauses. Okay. Each of these clauses had some number of variables. If you had randomly assigned true or false to the literals to the variables in each clause, then the probability that a particular clause is satisfied. So, we will denote it by AK. When we say that the event AK has occurred, that means clause number k is satisfied. Okay. So, the bad event would be that that clause is not satisfied. So, probability of AK bar is going to be 1 by 2 power k. So, the bad event happens with probability, if you just think of AK as the bad event. So, when AK occurs, it means that clause is not satisfiable. That happens with probability 1 by 2 raised to k, because there is only one assignment which can make the formula go wrong. So, when we use this, we automatically place a bound on the number of clauses. Even if we place union bound, it means that the probability that one of the clauses is unsatisfied, okay, that happens, I mean, you can say by applying union bound, you will get something like m times 2 raised to k. Okay. So, the number of clauses that you could have is something like 2 raised to k, but here we have a much more relaxed requirement. We do not bother about how many clauses are there, but if no variable appears in more than these many clauses, then we know that there will surely be a satisfying assignment. How do we prove that? So, again, our events are the same. AK means the kth clause is not satisfied. We need to say that probability of AK bar intersection over all k is going to be greater than 0, or 1 minus 1 by d plus 1 the whole raised to n. That is what the lemma states. But in order to apply the lemma, we need to show that the preconditions are true. So, first condition was the probability of any AK, we know it is exactly 1 by 2 to the power k, this we will call as our P. Okay. If you look at the dependency graph, look at two particular clauses being satisfied or unsatisfied. Now, if there are exactly k literals in it, so the number of other events to which these could be connected, okay, the maximum number is, if you look at two clauses, they are connected only if there is some kind of dependency between them. If their variables were completely different, okay, then there cannot be any connection. But we have a bound on variable sharing. Okay. Each variable can occur in at most 2 raised to k minus 2 clauses, and there are k variables in each clause. So, each clause can be connected to at most k times 2 raised to k minus 2 divided by k clauses. So, this is a bound on the number of other events on which the event AK could be dependent. Okay. This k and this k are not really related, let me just call it as AR. Okay. So, that means D is equal to 2 raised to k minus 2. Okay. Now, the condition that we wanted was E times P is 1 by 2 to the power k times 2 raised to k minus 2, that is 2 raised to k by 4. This should be less than or equal to 1, which it is, because E is less than 3. So, 3 by 4 less than 1. So, we know that in this case there will surely be an assignment which satisfies all the clauses. We will stop here. This is the final part of our lectures on probabilistic method.